Today we are going to talk about optimization, which is the main topic for this week. So let's get right into it. First of all, what is optimization? So optimization refers to the idea of maximizing or minimizing things. So someone might give you a function like f of x equals this function right here, x minus 0.9 squared, and say, how can I minimize that function? How can I make f of x as small as possible? And that problem is called an optimization problem because we're trying to minimize something. In this case, something squared can never be negative, so the smallest you could make f is 0 when you set x equal to 0.9, and then you get 0.9 minus 0.9 squared is 0. So the solution to this optimization problem, the minimum, is 0, and it occurs when x equals 0.9. So that was an example of a continuous optimization problem because x could vary continuously. It could just be any number. And we're going to talk a lot more about continuous optimization in the next course I'm going to teach Supervised Learning 2 in January. But today we're going to talk about discrete optimization, which is a case where x, the variables that we're allowed to change to make something big or small, cannot be any number continuously varying, but it can just be from a discrete set of options. So, for example, in this next bullet point, I'm saying, well, x is confined to an integer. So x could be, 0, 1, 2, 3, negative 1, negative 2, negative 3, but it can't be anything in between. So that's called a discrete optimization problem. And for this case, if we restrict x to integers, then the smallest we can make it is actually not 0, it's 0.01, because we'll set x to 1, 1 minus 0.9 is 0.1, 0.1 squared is 0.01. So we're going to focus on discrete optimization today because that's really the more algorithms and data structures type of thing that is thematic for this course. So here's a running example we're going to use for the next 10 or 20 minutes. We're going to look at length 8 strings of letters, so 8 letters in a row. And we're going to try to find the one that contains the most English words in it. So, I guess this one only contains the English word a. This one, I don't know, maybe doesn't contain a lot of English words in it either. But we're going to try to find the string that has the most English words in it. So the first question is with discrete optimization problems. Well, sometimes there's infinitely many possibilities, like above, x is an integer. But usually, at least in the algorithms and data structures flavor of discrete optimization problems, usually there's a finite number of things, of options or configurations or inputs. So in this case, we can actually count how many options there are, because the first letter could be A, B, C, D, E, all the way up to Z. So there's 26 things the first letter could be, 26 things the second letter could be, et cetera, et cetera. So we actually have 26 to the power of 8 options, which is a pretty big number. I don't even know what that is. Some bunch of trillions. So a lot of options. And so method number one for solving these kinds of discrete optimization problems with finitely many possibilities is just try all of them. So try A, count the number of words in it. Try A, B, count the number of words in it. And for a mere that many operations in your loop, you can definitely solve the optimization problem because you've tried everything and just taken the best one. So the whole point of the field of optimization and the kind of things we're going to talk about is that's not usually going to cut it because there's usually just too many possibilities and we need to talk about something more clever. But for now, let's just stick with the brute force for a minute so we can get into the spirit of discrete optimization. Any questions or comments so far? Okay, so what are the ingredients to make an optimization problem? When can I call something an optimization problem? Well, there's a few things you need. One is a specification of the space of possible inputs. We just did that. We said it's 8 letters in a row and they're all lowercase English letters from A to Z. And the next thing we need is, given one of those inputs, like A, B, C, how good is it? That's called an objective function. It's a function that turns one of those inputs into a score. And then we can find the input with the best score. So our score for this problem is the number of English words in one of those strings. So that is our objective function. And we just, by convention, it doesn't really matter maximizing or minimizing, but we have to say which one we're doing. So in this case, we're maximizing. If our score is the number of English words, we're maximizing it. So now we have our optimization problem. OK, let's solve it. So the first thing I'm going to do is just from this random place on GitHub that I found online, someone put a list of the 1,000 most common English words. I'm just going to use that as my dictionary of English words. I tried it with a bigger list of English words that had, I don't know, 100,000 words. And it was just very silly because there's a lot of things that are considered English words, like the letter T by itself. It was just weird. So these 1,000 common words will hopefully get the job done. So you can see. It's a set. OK, yeah, reasonable looking things. OK. Right, OK, so now what I need is a Python function that counts number of English words in a string. So the details of my code here are not very relevant, but basically it just looks for all length 1 substrings. Is this an English word? 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 And then it looks for all length 2 substrings. Is this an English word? Is this an English word? Is this an... And then all the way up to the whole length 8, which is the whole thing. Is that an English word? So that's what the loop is doing. And then it's just adding them to a set. So it's keeping track of all the words that appear as substrings of the input string. And then it's returning that set. So that's what this Python function does. So for example, in the 8-letter string, the apple, there are 4 English words. Again, these are just the 1,000 most common words that we're restricting ourselves to. So a, apple, he, and the are the 4 words. So the apple is probably not going to be our optimal string. We're probably going to be able to find something better that has more words in it than just 4. But how are we going to find that better string? Well, we're not searching through 200 trillion or whatever that number was, because that's going to take too long. Although there's perhaps no better way here. OK, so now my objective function. So my objective function is all it does is calls English words in string of x and returns the length of it, because that tells me how many. I don't really care what the words are when I'm computing my objective function. It's just I want the most words. So the thing I'm maximizing is the number of words. And so the length of that thing, in this case it would return 4, is my objective function. So now we're in pretty good shape because we have our objective function coded up in Python. And we could just call this Python function objective fun on each of those 200 trillion strings, get the biggest one, we're done. Great. So questions or comments about this? Yes, Mohammed.
Is the order here matters?
What do you mean by the order?
The words, for example, can I pick the last letter and then go and pick the first?
Oh, yeah. The order does matter. So you can't just take any of these letters and reorder them. I mean, the way I've defined the problem is it has to be an actual substring. So yeah, they have to be. So for example, maybe app, if I went beyond the 1,000 most common words, would count, but you can't scramble them. Okay, yeah, for this made-up problem, which is just for teaching purposes. Okay, so the objective function for the apple is 4. We were trying to find something better. Okay, so I don't actually want to run that loop over 200 trillion or whatever that number was things, because it'd be too slow. So I'm just going to restrict myself to only allowing the letters A, B, C, D, and E, so that instead of 26 to the power of 8 possibilities, we only have 5 to the power of 8. So what I'm basically saying, I'm actually admitting defeat. I don't have for you a way to solve the real problem, because it's not the type of problem where I can easily come up with a more clever algorithm other than just trying everything. Later today, we'll talk about other problems where there are more clever ways other than just trying everything. For this English words thing, at least off the top of my head, I don't actually have a better algorithm than brute force, so I'm just going to make the problem easier for teaching purposes. OK, So this function here is stolen from one of the optional questions on Lab 2. You can just ignore the code, but the important thing is that it just takes all possible combinations of some letters that you give it. So I'm just giving it the letters A, B, C, D, E. Again, I'd love to give it all 26 letters, but it would be too slow. So I'll just give it A, B, C, D, E. And this get inputs thing is just giving me all length 8 strings involving the letters A, B, C, D, E. And then I'm just going to loop over all of these and call my objective function and see which one is best. OK, so we saw map last class. So I'm going to map objective fun onto inputs. That means call the objective function for every input. I'm going to turn that into a list. And then I'm just going to take the maximum. OK, it's still looping over 5 to the power of 8 thing, so it's not instantaneous. OK, so we get 5. So 5 is pretty impressive because, again, we're just restricting ourselves to A, B, C, D, E. I'm sure if we allowed all 26 letters, we could get way more than 5, possibly a huge number of English words, but it's going to be too slow. So here is the string. A, A, B, E, D, A, D, D. Sorry for the scrolling. And here are the words. So can you imagine coming up with this by hand? Yeah, it's not going to happen, I'm guessing. So basically, we came up with an optimization problem, and we solved it with brute force, which, again, is not a very interesting method for solving it. But we just took all the possible inputs. There weren't that many of them in this case. We applied the objective function, and we just said, what is the max? It's 5. What is the argmax, meaning what is the string that achieved this? And we got something kind of cool that had these 5 words in it. Questions or comments? And you can play around with this later. You can add the next letter, F, and you'll probably get more words and do all these kinds of things. OK, so another question is the solution unique? Because that's often a question we ask ourselves in optimization. What does that mean? It means, is A, B, E, D, A, D, D the only length 8 string using those letters that gets 5 words? Because maybe there's a bunch, right? We know there's nothing that gets 6 because we tried all of them and 5 was the most we got. But maybe there's more of them that get 5. So what I could do is I could sort the scores. And I can see there's actually a bunch of 5s. I'm not checking how many, but it seems in this case the solution is not unique. You had something like that in your lab 3 with the graphs where you were finding the most distance between nodes, and you were taking all pairs of nodes and finding the ones that had the longest degrees of separation, and then your function was returning all the ones that had that largest distance. It's kind of like this. You didn't have a single unique solution, so you were returning all the pairs. So you were actually solving an optimization problem in that lab, and you were using this method too. You're using brute force. You were just checking all possibilities and finding the best ones. But what we really would like to do in the field of optimization is move beyond checking all possibilities, because as you saw, for example, for those who tried the optional question in lab, your real data set is often going to be too big that you can't actually try all possibilities. Questions about this? OK. So another example, finding the shortest path between 2 nodes in a graph. So that was something that we talked about that appeared on the lab as an optional question as well. And so we can just frame it as an optimization problem. What are all the possible inputs? Well, there's all possible paths from A to B. What's the objective function? It is the length of the path. And what are we doing? We are minimizing. So a lot of things we've been talking about, you could actually think about as optimization problems. We just did not use those words yet. OK, so there are many ways to solve an optimization problem. brute force is looking at all possibilities. We did that for 5 English letters. We couldn't do that for 26 English letters because it's going to be too slow. Think about data sets the size of the Facebook graph. Things involving all pairs or whatever are typically going to be too slow. So we want better algorithms. And sometimes there are better algorithms. So for example, that breadth first search thing for finding the degrees of separation between 2 nodes is a better algorithm than just looking at all paths between 2 nodes and saying which is the shortest path. That would be super slow. Okay. Next stop, constraints. So there's kind of another ingredient to the optimization problems that I skipped over. So there's the space of inputs, the objective function, and whether you're maximizing or minimizing. So there's also constraints, which plays into the space of inputs, which was our first ingredient. And so, for example, instead of all length 8 strings, that's what we just had. What if we had all length 8 strings such that each letter appears at most twice? So when we add constraints, we're making the problem harder because we are removing possible inputs. We're saying this is not allowed. And so you could only get as good a solution or a worse solution when you start adding constraints because you're just disallowing possible inputs. If I disallowed all the 5s, then my best might become 4. I might get a worse answer. Or if I didn't disallow all the 5s, then my solution might still be 5, but maybe I'm knocking out some of those best solutions. So for example, here, A, B, B, C, C, D, D is fine. A, B, C, D, E, F, G, H is fine. But this one with 3 A's and 3 B's is not valid, and the terminology we use is that it violates the constraint, because the constraint said each letter appears at most twice. You're not allowed to have the same letter appearing 3 times, which honestly is probably not really going to affect this much, because that's probably not the way to get a lot of English words, but maybe it is. Okay, so yeah, there's 2 ways of thinking about constraints. You could think about constraints as just part of ingredient number 1, which is specifying the possible inputs, like, well, it's just those inputs are not allowed. But it's often helpful to think of constraints as just like a separate ingredient in your optimization problem that can often help us think about and use software to solve problems, and you'll see that in a minute. Okay, so yeah, I just added optional a set of constraints. And what is a constraint in terms of a Python function? So the objective in terms of a Python function took in one of those inputs and gave back a number, which was like the score. A constraint as a Python function takes in one of those inputs and returns true or false. Is that OK, or is it not OK? So our particular constraint here is going to look like this. It's going to count how many of each letter are in the string, take the max of that, and then check if it's less than or equal to 2 or not. So I have 3 A's, 3 B's, and 2 C's, 3, 3, and 2. The max of that is 3. Is that less than or equal to 2? No. So I violated the constraint because I have 3 of some letter and I'm not allowed. So the particular line of code here is not so important, but understanding what this function does is important. It takes in one of these inputs, a length 8 string S, and it just returns true or false. Is that a valid or an invalid input based on this constraint? Any questions about that? Okay. And, oh, yes, Ryan.
Instead of the objective function, why is part of the specification of function?
Why is the objective function a specification of the optimization problem? Because to define the problem, you have to say what function is it that you're maximizing or minimizing. Without that, I would just say, give me the length 8 string with the most, what? With the most English words in it.
The optimization problem was finding all the words, but counting how many of them there were.
The optimization problem was find me the length 8 string with the most English words in it. That was, so the most English words in it part, that's the objective function. That's telling us how to define a good string versus a bad string. Okay, so about objective function, you just have one of them. Constraints, you can have as many as you want. You could have 10 constraints, and they all have to be true. They all have to be satisfied in order for an input to be valid. So you can have each letter can appear at most twice, and you're not allowed any Fs. And if you have an E, then you can't have a Q, and et cetera, et cetera. You can have lots of constraints. Okay, so let's see. Yeah, I just have some tests. So this one should satisfy the constraint. This one should violate the constraint. And this is not even that important. Okay, so we can now solve the constrained optimization problem. So again, here's our, again, only using A, B, C, D, and E just for speed reasons. Here was all of our strings before, all of our 5 to the power of 8 possible strings. Again, 5 because there's 5 letters, A, B, C, D, E. 8 because there's 8 spots here, length 8 strings. And here's what I'm going to do now. I'm just going to delete all the ones that violate the constraint. That's what this next line of code. It's a list comprehension that says take all the strings and inputs, but only if that function returns true. And by the way, let me add here that this is 5 to the power of 8. And this better be something smaller, because I have thrown away, in this case, actually, most of the possibilities, because apparently most of the possibilities violate that constraint, like A violates the constraint because there's too many A's. So I've narrowed down my space of inputs, and here's the first 10, and you can see they all satisfy the constraint. And now I can do this brute force thing, and hey, this time the best is 4. So it turns out that by constraining them, I actually did remove all the solutions that had 5 words in them. So the solution to my constrained optimization problem is not as good as the solution to my original optimization problem. Now I can only get 4 words. A, B, A, D, B, E, D, C gets me these 4 words. Questions? Okay, so the constrained optimum can be equal to or worse than the unconstrained one. In this case, it's worse. Might be different. So yeah, the word bad was actually not in our unconstrained solution. In general, the constrained solution might have nothing to do with the unconstrained solution. It might look completely different. There's no promises that it's like the 5 words I had before and I just removed one of them and now I had 4 words or anything like that. All bets are off. So here I got this. It's probably not unique. Again, I didn't check. We can have multiple constraints. Talked about that. And that's pretty much that. So questions about constraints?
Is that a valid solution because the C shouldn't be repeated twice?
The question is that a valid solution because the C shouldn't be repeated twice? So it is valid. We didn't say you have to have 2 of every letter. We just said you can have at most 2 of every letter. So you can have 0 of a letter, 1 of a letter, or 2 of a letter. And I'll just scroll up for a minute. That's reflected in this less than or equal to right here, where n is 2 in our case. Any other questions? Tom?
So is the framework for this essentially develop your input and then narrow it down to the constraint and then map it through the abstract function? Whatever the constraint input is?
Well, you'll see in a second. No, what I just did isn't the general way of doing things because I've done brute force, which you typically can never do. So the really point of what I showed you is just so you can internalize what is a constraint, what is an objective. And other than that, you'll probably never do things like this because it'll be too slow. Okay, I'm over the moon right now because we are on time, which rarely happens. So this is great. Let's continue. So for the next, I don't know, half hour or so, we're going to go with this running example about TA assignments. This is something that it's just quite similar to something I actually do. So every semester, a bunch of people apply to TA for MDS, and they say which courses they're interested in TAing for, and we have to decide, okay, which TA is going to be for which course based on a whole bunch of information. So I have this CSV in the folder. I just updated it right before class, so again, you may want to pull. I just deleted one line of it. So here's a list of made-up TAs, and this is actually not that different from the real thing when we're doing this. So here's a bunch of people. Here's what days they're available on. Here's their proficiency in R and Python. And then here's a list of courses they are willing to teach, and another list of courses that they would love to teach. And on the other hand, I have another table, which is, oh, can people at the back see these tables? Yes and no. I will average that to a no. Okay. I think this is about as much zoom as I can go for. Okay, and this is the course table. So on the other hand, I have 12 courses for the semester. And, well, these columns don't really matter, but I have what days the labs are on. I have the languages that are used in the courses. And I have what block the courses are in. So those last three columns are actually relevant for the optimization problem that I'm about to solve. Okay, so here is my goal. I want to match TAs to courses in a way that meets our needs as well as possible. As well as possible, that's our objective function. I have a fancier objective function when I do this for real, but here the objective function will just be maximize the number of times where the TA is enthusiastic about their course they're teaching. So some courses they're willing to teach, some courses they're enthusiastic. We'd rather them be enthusiastic. That's not a constraint. They don't have to be. It's not a deal breaker, but we would prefer that. So that's our objective function. And we have a bunch of constraints. So each course should be assigned exactly 2 TAs. Okay, now it's more like 4 or 5 this year, but each course should be assigned exactly 2 TAs. A TA can only cover one course at one time. So that's why this block column in the courses table is important. I need to know what block a course is in, because a TA can do programming and algorithms, but they can't do programming and probability, because those are in the same block. TA can only be assigned to a course they have listed as can teach or enthusiastic. So if they didn't list a course at all, then I can't assign them, because they didn't say they can teach it. And to cover a course, a TA must be available for one of the 2 lab days. So this is a bit of a simplification of the real constraint, but if the labs are Monday, Tuesday, and they're available either of those days, we'll just say that's good enough, and that'll be our constraint for simplicity. And then I think right below here, right, and we want to maximize the number of assigned courses that the TAs are enthusiastic. I'm going to zoom back out. Okay. So any questions about this optimization problem? Victor.
So how can you give preference to something if it's not a constraint?
How can I give preference to something if it's not a constraint? Right. So that is precisely what the objective function is for. So constraints are, it has to be this way, and the objective function is preference. So going back to the words, it had to be that the words, you're only allowed 2 of each letter. We made that a constraint. And we preferred to have more English words in it than fewer. So we preferred a string with 5 English words to a string with 2 English words. And then when we solved the problem, we got the most preferred thing that had 5 words. So our objective function here is precisely telling us about our preference. We want more enthusiastic TAs doing courses. And then the constraints are just non-negotiables. For Khan.
So how about if you want to blend the TAs enthusiasm with TAs skills that are like a combination of?
Yes. What if we have a combination of preferences? So in fact, that actually happens. For example, you saw that I know what language the TAs are familiar with, and I know what language the courses are taught in, and I would rather put someone who knows Python on a course in Python, and I would rather really avoid someone who put 0 experience on R in an R course or something like that. So yes, sometimes you have multiple objectives, and the easiest thing to do is just to combine them into one big function. So my objective might be the number of enthusiastic TAs plus the number of people in a language they're comfortable with. And then it kind of balances both of them. And you could say, you could change the relative importance of those things by basically multiplying one of them by a bigger number. So enthusiasm score plus 100 times R in Python score will mean I care more about the R in Python score than the enthusiasm score. So that's typically a type of trick you would play to combine multiple objectives. Here we'll just stick to one objective. Let us formally take this problem that we've described in words and encode it mathematically. This is kind of the meat of today's lecture is what we're about to do. And it's quite not that intuitive necessarily. So we have plenty of time. First, we're going to be using a library called Pulp, P-U-L-P. This is a Python linear programming. We'll talk a bit about what that means in a second. But what I'm going to be doing right now is interspersing the code and the math as we build the problem. So the first thing I'm going to do, this is just the syntax for this Python package to say initialize a optimization problem, and you just say if you're maximizing or minimizing. So in this case, we're maximizing because we're going to maximize the amount of enthusiasm that we have over all courses. So that's what this is. Now the next thing we have to do is set up our decision variables. And this is maybe one of the most unintuitive parts here, because you might say that, well, what are our variables here? They are the list of courses for each TA. So for a given TA, Bob, you could have, Bob could have any of the 4 courses in block 1 or none, any of the 4 courses in block 2 or none, any of the 4 courses in block 3 or none. And then if you wanted to list all possibilities, you'd have to take the product of all those things. You say this in block 1 and this in block 2 and this in block 3, or that in block 1 and this in block 2 and that in block 3. And you would just get this crazy list of things that Bob could do. And then you have to say all the combinations of what Bob could do with what Alice could do. And we'll basically go insane. So the strategy that we need to do here is we do this with binary variables. And this is a very common trick in optimization. It may be unintuitive, but it's critical. So x, ij, is going to be 1 if the TAI is assigned to the course j and 0 otherwise. So in other words, we're going to think about it as a table like this. We have all the TAs, all the courses, and we're going to have a 1 there if that TA is assigned to that course, and a 0 if that TA is not assigned to that course. Now, not all possible tables satisfy the constraints. For example, if everything was filled with 1s, that wouldn't work, because a TA would be doing 2 things in the same block. And if the table was all 0s, that wouldn't work, because the courses wouldn't have any staff. However, think back to what we talked about before with the letters. That's why I wanted to say constraints should be kind of separated in our mind. It'll help us think more clearly. This is the best way to set up the problem, the table of 1s and 0s. And then we add on the constraints after this that starts eliminating, well, not all possible tables of 0s and 1s are allowed, because some of them violate the constraints. Questions about this?
Are you saying that we start off with a randomized table and then we start?
Not exactly. So Ryan's question is, do we start off with a randomized table and do stuff from there? So that is how some optimization algorithms work, but we're not even thinking yet about how to solve the problem. We're just thinking about our ingredients for the problem, which are what are the possible solutions. And in fact, we're barely going to get into how it really solves the problem with this Python package. But yes, you could, if it helps you to think about it that way, then sure. Okay, so here's the code for that in Pulp. And you don't need to memorize this, you can just refer to it later, but basically I am making a cross product of all the TAs by all the courses, and I'm saying the minimum is 0 and the maximum is 1, and the variables are integers, which basically is another way of saying they can only be 0 or 1. And by the way, how many possible inputs are there? Oh, I think I deleted one of the TAs, so there's not 11 anymore. 4, 5, 6, 7, 8. It's only 10 TAs. We need to do better than this. Yes, okay. So let's just think about it, how many possible tables like this are there? Well, we have 12 courses and 10 TAs. Ugh, sorry. Okay, so we have 120 entries in this table because it's a 10 by 12 table. And each of those entries in the table could be 0 or 1. So the number is 2 to the power of that. 2 to the power of 120, which is that. So that is how many possibilities we have to search through. A lot more than what we had with the strings. And so you can just imagine, I mean, don't even think about brute force. And this is only 10 TAs. I mean, think of a data set where you have thousands of rows, right? So amazingly, we're actually going to be able to solve this kind of problem. And let's skip this for a minute because it's outdated. Okay, so we have a lot of possible tables. Let's set up the constraints. So here's the tricky part. We have to change our English constraints into math, and then change our math into code, and we're going to stick that code into our pulp library. And by the way, basically the strategy here is going to be set everything up with the pulp library and just call solve and let it solve the problem. And it's going to solve the problem a lot faster than doing that many things because it uses very clever algorithms that takes advantage of the linearness of the problem, which is not something we're going to go into too much. But even just taking what we talked about in the last 10 minutes, like these constraints in our head, and just turning them into the right math and sticking them in the code is actually quite a challenging and not trivial at all problem. So you'll see that in a minute. So first of all, each course should be assigned exactly 2 TAs. Let me scroll up to our table. Each course should be assigned exactly 2 TAs. What that means is that the sum of each column needs to be equal to 2. Because each column is all the people assigned to a course, and the sum of that column is the number of TAs assigned to that course. So what we want to say is for every column, because it's true for every course, for every column, the sum of that column equals 2. Very important point. Any questions about that? Okay, go back down. Okay, so here it is. For all courses J, the sum over I of xij, that means the sum over the columns, because I is our TA, so we're summing over all TAs, over all rows, equals 2. And here's how it's going to look in code. For every course, because this has to be true for every course, not just 511. And then there's some very weird syntax that pulp uses that we just need to get through. So when you want to take a sum, you have to use their special summing function. You can't just use regular summing. That's just something we have to deal with. And here's the kind of meat of it inside the loop. I'm saying for every TA, in other words, for every I, summing down that table, for that course, that sum has to equal 2. And so when I do prob plus equals in pulp, that's the syntax for adding a constraint to the problem. And so I have a constraint per course. I have the 511 has to have 2 TAs, the 521 has to have 2 TAs. So I'm looping over all courses, and inside the loop I'm adding a constraint, and now I have 12 constraints, one for each course, saying that course has to have 2 TAs. Someone must be confused here. Yeah, Tom.
Can you explain to me the XTA?
Yes. Yes, the XTA course. So X is, so basically we have this table. Alice, Bob, etc. 511, 521, etc. And I could have set up the index for X that it was like a numerical index, like this is X00, X01, X02, X. x10, x11. But I just set it up as a dictionary style indexing instead. So it's basically a dictionary of dictionaries because it's just a bit easier to keep track. So I actually index it x of Alice of 511. And then it's just a bit nicer to keep track of what is what rather than the integer indexing. So you could think of x as a dictionary of dictionaries of these potential ones or zeros. Any?
So in the beginning, you created that random table that Ryan was asking about. So are you doing this next part one time for every table?
Okay, right. So the random table, by the way, is not actually going to be used by my code. It was purely for illustration for you all. So I'm not actually using that random table later on in the code. What was the other part of your question?
But how do you, like, what is this part that you've just written going to be applied to?
Right. So no, that's an excellent point. We're doing something that we maybe haven't yet done in the MDS program that we will do a lot more of later, which is we have lines of Python code where nothing is actually happening when you run that line of Python code. So there is no computation resulting from these lines of Python code, but rather the people who designed Pulp decided that when you want to specify the problem, instead of, so for example, you could give it a file, like a text file that had all the information, here's the objectives, here's the constraints, you could just say, hey, Pulp, here's my text file that contains all the math for my problem, and it could ingest that file. But instead, the designers of Pulp decided it's going to use actual Python code in order for you, the user, to say what your problem is. So we're going to be running, dozens of lines of Python code in the next 10 minutes. And all they're doing is they're changing that prob object, which is like the problem, the optimization problem. We're just saying, and we have this constraint, and this constraint, and this constraint, and the objective. And the prob object is just getting updated. And then at the very end, we're going to do prob.solve, and it's going to do all the computation in that one line of code at the bottom. So we're actually going to see that again later in the MDS program, but it's a very, very good point. That's something we're not used to, is these lines of Python are not doing computation. They're just giving information to that object so that when it's ready to do the computation, it knows what your problem is, right?
Okay, so that thing is kind of saying, like, let's throw all the different combinations of TAs and courses, and then the sum of something should be 2. And if TA and course is always different, how can it ever be 1 and 1? I'm not really understanding the formula itself.
So you're looping through courses. So first you start at 511. And then there's basically a comprehension inside there, which is what's highlighted, which is saying, OK, X TA of course. In that inner loop, the TA keeps changing, but the course is staying the same. So course is 511 in the other loop. TA is going Alice, Bob, Carol, et cetera, et cetera, et cetera. And it's basically forming all those into a comprehension and sticking them into LP sum, which is basically like their version of summing. And so that says the sum of all these variables needs to be equal to 2. But the weird thing is those variables don't exist yet. Like, it hasn't yet been decided if those variables are 0 or 1. So in a way, of course, you can't use regular Python sum because it's not numbers you're summing. It's like hypothetical numbers. It's these decision variables. And you're saying when you get there, the sum of all those things, when you're done, had better be equal to 2 for all courses. Kenneth.
Just in the statement where it has plus equals and equals.
Yeah.
So the equals has a higher hierarchy compared.
Yeah. Yeah. So that's a fair. Thank you. So this may be more clear. The thing on the right is like a Boolean. Again, it's not evaluating to a Boolean right now because it doesn't know yet, but we're just communicating through Python code what we're trying to get across here. And then, yeah, the plus equals just says add this to the list of constraints. Jarvis.
This might be helpful that you can print the problem, which would show the constraints.
OK, let's do that. Let me run this. Oh, cool. Maximize none. We don't have an objective function yet. This is great. Thanks, Jarvis. Yeah, so constraint number 1, C1. Alice 511 plus Bob 511 plus Carol 511 equals 2. That's exactly what we want. That's that column here for 511. And then we have another constraint, constraint number 2, which says Alice 521 plus Bob 521. Yeah, that's really nice. Thank you. Any other questions? Victor.
At the beginning, we defined the prop, but we didn't give the objective function there.
Correct. I'll put the objective function at the end. So as far as pulp is concerned, it doesn't matter what order you specify the constraints or the objective, because it's all just setting it up, setting it up, setting up, and then only when you call prob.solve does it actually solve given everything that you've given it. Yeah, so we will get to the objective. Great. Okay. Oh, very nice. Yeah. Integers between, holy cow. Okay. There we go. Okay, those are all our variables. Thanks. Okay. All right. In pulp, we use the plus equal syntax to add a new constraint to the optimization problem. No code is actually being run here. We're just specifying it. Da, 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 da. You'll see this again in 5.7.2 when we do TensorFlow. It's the same kind of pattern where you have a bunch of lines of code setting it up and then the line of code to actually do the work. You'll see that in the Bayesian inference course, 5.5.3, same kind of thing. So it's a bit of a pattern. Okay, next constraint. Well, TA can only cover one course at a time in a given block. So here's what that is, 5.4.2. So actually, our big table is really kind of 3 tables next to each other. So I don't remember all the courses now, but our big table is really this with all 12 courses. But for this constraint, we need to think about the blocks separately. So what this is saying is that the sum here cannot be more than 1. Alice could do nothing in block 1, that's fine. But Alice cannot do 2 things in block 1. And this sum also cannot be greater than 1. And this sum can also not be greater than 1. And this sum can also not be greater than 1. Because again, a TA cannot do 2 courses at the same time. So by the way, before we had an equality constraint, equals 2. We have to have exactly 2 TAs per course. Now we have an inequality constraint, which says less than or equal to 1. So a TA could be doing nothing in block 1 or 1 thing in block 1, but not more. So here it is. For all blocks B, we require that for all courses in the block, that's what this notation is trying to say, for all courses in the block, the sum of all those x's is less than or equal to 1. So here's the code. For all TAs, because every TA is going to have this constraint applied to them, loop, 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 loop. For all blocks, block 1, block 2, block 3, we add a constraint. Yeah, I just changed this code a couple days ago after seeing Tom's lecture. So using this dataframe.query. So I'll just grab the courses that are actually in that block. And then I'll say the sum of x for all the courses in the block, that's one of these things here, is less than or equal to 1. Questions about this? Yes, Tani.
X, the @ sign.
The @ sign, I got that from Tom. That's taking the, that's a specific to df.query that it's saying take the variable called block. So this, this one is the column name block in the data frame, and this one is the Python variable block from my loop. Yeah, maybe I should have named those different things. Whose hand is that? Gaurav.
Are we creating any list or something of courses in block of that type, where we are looking for the courses in a particular block?
Yeah, so that's what this middle line of code is doing. So this line of code here is saying just grab the courses in that particular block, and then I'm using that variable courses in block on the next line so that my sum is not over all 12 courses, but only over those 4 courses. Because it is okay to TA here and here, so I don't want to sum over the whole thing. I just want to sum inside that block. Annie.
For best practices, if there was one TA that you could have two for the block, would we, like, if this was a different scenario, would we just add like another row and call it like Alice 2? Or is best practices to write something within the function that...
Yeah, I mean, yeah, if this didn't apply to someone, you could be like, if TA equals Alice, continue or something, then it would just skip Alice. That's what I would do. I think Ahmad? No? You had a raised hand? Yeah.
Don't we need to put any constraint on the greater than 0?
Do we need to put a constraint on greater than 0? Good question. So we don't, because at the very beginning, we said that x values could only be 0 or 1. And so that kind of takes care of that for us. We can't have negative values because of that. So yeah, we already dealt with that earlier. And then there was one more, and I thought, no? Aha. Vignesh. We'll get to the availabilities. Yeah, in fact, maybe that's next. So let me run this code. Done. Okay, a TA can only be assigned to course they have listed as can teach or enthusiastic. So if Ivan did not list 512, we cannot assign Ivan to 512. So here's what I'm going to do. For every TA, for every course, if the course is not in, and now I'm using df.lock to get this is the TA's data frame, TA's df. So that's the data frame about the TAs. The row for the TA, the column for can teach. I think Tom would not like that. I think we're supposed to do this, maybe? I don't remember. Okay, this might be more preferred. The TA row, the can teach column. So if the course is not in their can teach list, and the course is not in their enthusiastic list, I mean, they didn't list the course anywhere, I cannot assign them to that course. And so, again, thank you, Kenneth. I think might be a little more clear like this. Then that particular x must be equal to 0. I must set this to 0 if Bob did not list 521 as something Bob could teach. Derek.
Is the enthusiastic part necessary because
Is the enthusiastic part necessary? So the way I typically do it, yes, like sometimes TAs will not relist. They'll just have two separate things, like can teach and enthusiastic, and they won't have the enthusiastic ones also in the can teach list. So just to avoid that possible miscommunication, it's safer to do it this way. But yeah, I could also do some data wrangling in advance to like copy those all over and then simplify this code. Other questions? Sam.
How do we know this is saying that it cannot be 0? Because in the other ones we were saying, or are we setting this up as a constraint? Is that why we're saying equals 0 at the end? I was confused with equals 0.
Yeah, so equals 0. So let me scroll back up. Oh gosh, not even going to try. Okay, the equals 0, that's just the pulp syntax to say that thing has to be equal to 0. Like in normal Python, equals 0 would return a Boolean. Again, this Boolean is not being computed right now because we don't know what x is yet, but that's just the syntax that they decided. So before we had equals 2 to make sure there were 2 TAs per course, and here we had so before we had the sum of the column equals 2 to say you have to have 2 TAs. Of course, now we have this particular one equals 0.
I guess I was confused because this one, it cannot be 0, right? That's kind of what
Oh, no. It must be 0. It must be 0 because, so I could say, if they're willing to teach something, I'm not forcing them to. All I'm saying is if they're not willing to teach something, I cannot assign them. And 1 means the person is assigned, and 0 means they're not assigned. So I'm not actually, I want to force things to be 0, not the other way around. Because if Bob can't do 521, boom, 0, no matter what. If Alice can't do 552, boom. That's like set in stone before I even start. Does that make sense?
Yeah.
Okay. Mohammed.
Is the order we are putting this constraint matter?
Sorry, start again.
The order that we are putting.
No, the order doesn't matter. You can specify the constraints in any order.
So like all we have did is like
Hold on, I forgot your name.
Luke.
Luke. Yeah.
So like all I have done like is I want to solve for x, right?
Yes. All we want is to solve for x. All this work is just going to, all we want at the end is x, correct? Okay. Now availability, someone asked about that earlier. So to cover a course, a TA must be available for one of the 2 days. Again, that's not really good enough because maybe all the TAs are available on Thursday and no one on Wednesday, but just for our purposes, this is a bit simpler. So, okay, at this point, I think the math is actually harder to read than the code. So let's just go to the code. So for every TA and for every course, I'm looking at the course data frame, and I'm getting the lab days, which will be like MT for Monday, Tuesday, and then 0 is getting the first one, so like Monday. So if the first lab day, say Monday, is not in the TA's availability list, so say the course is Monday, Tuesday lab. If Monday is not in their list of availability and Tuesday is not in their list of availability, they can't TA for that course. And again, I think this goes back to what Sam is asking. We're kind of specifying it backwards from how we say it in English. We're saying they have to be available for one of the 2 days. That's what we say in English. But in the constraints, we're saying if they're not available on day 1 and they're not available on day 2, then they can't TA for the course. So this code over here it's just the exact same, but okay, hopefully that works. So if the first lab day is not in their availability and the second lab day is not in their availability, then they cannot TA for that course. So pretty similar to the one we did above. And now we're done with the constraints, and now we finally get to the objective as promised. So our objective is we want to maximize the number of assigned courses that the TAs are enthusiastic about. So here's what I'm going to do. Basically, let me take another color, blue. So each TA has a list of what they're enthusiastic about. So maybe Alice is enthusiastic about 511, 521, and 512. And maybe Bob is enthusiastic about 511 and visualization 2. So you could think about enthusiasm as just spaces in this table, because each TA listed the courses that they're enthusiastic about. And basically, every time we get a 1 in one of these blue circles, that is a thumbs up. That's what we're trying to get. We're trying to get as many 1s in these blue circles as possible. And of course, we can't just fill the whole table with 1s, because that would violate the constraints, right? So there's this tension between the constraints and the objective. The objective would love to just fill the whole table with 1s, and then you'll get all the enthusiasm in the world. But no, that violates the constraints. So let's just look at the code first. Yeah, gosh. Should have written this in a bit more of a, oh well. Anyways, I made a nested loop comprehension, which I know is harder to read than a regular loop, but so be it. So basically, I'm looping through the TAs, that's the rows of this table. I'm looping through the courses, that's the columns of this table. But then I have this if inside of my comprehension that says only take the cases where that particular TA is enthusiastic. Again, I think comma here is the preferred approach. And then I'm LP summing X in just those spots. So basically, all the comprehension stuff is saying loop over rows, loop over columns. That'll get me every single spot in my table. But then I have that if that says if the TA is enthusiastic about that course, that's only taking me the blue spots. And then I'm just summing all the X's in those blue spots. Right.
So after you get all these sums, it automatically knows that go to the largest, like try to maximize it such that.
Yes, so a few things here. First of all, if I go to the end of this regrettably long line of code, you'll see there's no equals, equals, or less than or equal to like we had before. That's how you signal to pulp that this one is the objective rather than a constraint, because it's just prob plus equal and then a thing that'll become a number. And then earlier we said that it was maximizing rather than minimizing, so that's how it knows it's maximizing. Maybe I'll clean up this line of code later because it's very hard to read. Turn it into 5 lines of code or whatever. Okay. Questions about the objective? Victor.
Yeah, sorry, I don't understand very well how those you are saying with that line that that is the function, the optimization.
Okay. Let me. How much time do we have? Oh, very little time. Gosh, we end at 11. Okay. We'll have to come back to that. Yeah. Time flies. Okay. No. Yeah, that's fine. Okay. I'll clean that up later. But okay. The punchline is that once we've done all that work, we only have 4 minutes left. All I need to do is call problem.solve. And it says you solved the problem and it got something and it's optimal. And we got 16 out of 24 courses, or 24, there's 12 courses, 2 TAs per course, so 24 kind of slots. We got 16 amount of enthusiasm. And then I can just print out the results. So this pulp.value is a way of querying the results after we got them. And I just stick into a data frame. And there we have it. Here's what every TA is going to do. Alice is going to TA in block 2 and 3, but not block 1. Bob is going to TA every block, et cetera, et cetera. And I can also print it out by course. And here's my list of TAs by course. And notice that line of code prob.solve, like it didn't even take any noticeable amount of time to run. It just ran instantly. And you can go back and check all these things, see that it satisfies the constraints. But you can actually be sure that you could not get more than 16 amount of enthusiasm, because this thing guarantees me the optimal solution, and I'm pretty confident that if you did it by hand, you would have a hard time getting that optimal amount of enthusiasm. Evan.
What if we have multiple optimals? How do you
What if you have
multiple optimals?
Yeah, so the solution might not be unique, as we talked about earlier. There might be a bunch of configurations that are equal. It is just returning an arbitrary one. The solution probably isn't unique. That would be my gut feeling here. And it's just returning whichever one it feels like. Annie.
If you have multiple problem constraints and then you decide one of them you don't want anymore and you comment it out, because it's updating all the time, does it know?
Yeah, so the question is, if there's a constraint you don't want anymore, you would have to run the whole code from the beginning. So set up the problem, put in all the other constraints, but not that one, and then solve again.
That'll be it.
Yeah. Mohammed.
Are we still using brute force?
We're not using brute force. It's just, I'm running out of time because I only have 1 minute left in the lecture. But it can't possibly be using brute force because you saw the number that was this long of how many possibilities there were. So that would be too slow. It's using a much more clever algorithm. Maybe in my last minute, I'll just try to say very briefly how it's working. So basically, imagine it tries a particular configuration with 2 1s in here. That's not allowed. Alice cannot TA 2 courses in block 1. Brute force would try every possibility that had 2 1s here. There's still like a million possibilities that would have 2 1s here. But this thing basically knows, well, I've already violated the constraint. There's no point trying every possibility given that. You can start kind of pruning and throwing away whole parts of the solution space that cannot be feasible. And so that's like a very vague intuition about how it works. It's actually much more complicated than that. But because it knows things about your problem in a particular way, it kind of knows what the constraints are rather than just being given a function to say true or false. It can leverage that to be way faster than brute force. We are out of time. since this is last week of the course, I think I'll want to just finish this lecture. What's today? It's Tuesday. Lab is Wednesday, Thursday. Okay, I'll finish this lecture on Thursday. I'll run out of time on Thursday, and we'll sort it out in lab so that we get to everything. But yeah, we have to stop now. I'll see you soon.